Hey guys, it's Miss Miklos, and today we are kind of transitioning into talking about vectors. And so I want to start off by showing you guys a little clip.
Hey. I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh, yeah! Check out my new weapon. Piranha gun! Oh, yes! Fires live piranhas. Ever seen one before? No, you haven't. I invented it. Do you want a demonstration? Oh, ah! Goodness, it's so difficult sometimes to get the brain back inside of me.
So as Despicable Me so eloquently put it, a vector is a mathematical term for really a ray that has both length and direction. So that's what makes it different. It's not just like somewhere out in space. It actually has a specific starting point. And normally when we see an arrow, we think of that as going on forever, but a vector has a definite length. So it has a starting point, which we call our initial point, and it has a spot where it ends, which we call the terminal point. For example, here's a vector that has an initial point, there we go, of 0, 0. So it's starting at the origin. It has a terminal point at 1, negative 2. Okay, so pretty simple, but initial, we know that's where it starts. Terminal, that's where it ends. Now, we're really going to see a few different ways that we write vectors. The most common way is something that we call component form. And what component form is, it is the terminal point minus the initial point. So in this particular case, okay, we're going to take the terminal point, which was 1, negative 2, and subtract the initial point. So we're going to go ahead and do 1 minus 0, which we know is 1. And we're going to do negative 2 minus 0, which we know is negative 2. Now with component form, this is not an ordered pair. So what we do, we use these little brackets that look like less than and greater than signs to represent component form. Okay, so 1, negative 2 is really just telling us that it's going to the, I did not mean to erase her. Here we go. Then we're going to the right one and we're going down 2. Okay, so it's not necessarily a point of 1, negative 2. It is in this case. Okay, but it's really telling us what the vector is doing. It's telling us the direction of the vector. We haven't talked about length yet, but direction is definitely shown in our component form. The other way that we write this is something that we call linear combination form. Okay, and basically what that is going to do, it's taking a horizontal vector and a vertical vector. So we would say that this vector is 1i minus 2j. I'm trying to make these a little bit bold. Okay, because what we will often see with vector notation, we will sometimes see the vector written with like a V or whatever the name is of it and a little like half arrow on top. Or sometimes we will see it with just a bolder looking variable. So our book will kind of show both of these notations. And so it's important we are kind of aware of what we're looking for. So linear combination form is really saying the same exact thing as component form. The I coefficient is telling us right and left. The J coefficient is telling us up and down. So what you're going to find today is that for a lot of you, this information is going to be totally new. Others of you are in physics or have taken physics, so you're more familiar with the concept of a vector. Our actual math itself is not going to be that tough today. What makes it difficult is just the fact that it's completely brand new, and there's just a lot of new formulas and just information for us to know. And by formulas, they're kind of as tough as this. I like how little teeny it got there. But that's not a difficult formula to remember, yet at the same time, it's something we need to know. So number 1 tells us vector v has an initial point -2, 1 and terminal point 7, 6. Find the component form of vector v and linear combination form. For all of you visual learners out there, I'm going to start just actually by graphing this out. Now, in order to do this problem, you definitely do not need to graph. Okay, sorry, I'm just counting. The graph itself is just going to be something that can just show us what our answer actually means. So this vector starts at -2, 1, so I'm going to put a point there. And the terminal point is at 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6. And we know it starts at the initial, it ends at the terminal. So one way that technically we could find the component form is to count to the right. Okay, because it's moving to the right. That would be like the first portion of our component form, and then count up, and that would be the second portion. But we really talked about the fact that it is terminal minus initial. So I'm going to go ahead and do this by subtracting those two ordered pairs. Our terminal is 7, 6. Our initial was -2, 1. So I'm going to do 7 minus -2. And then I'm going to go ahead and do 6 minus 1. So I get 9, 5. So what that's telling me is that this particular vector is moving to the right 9 and up 5. And we could count it and see that as well. To find the linear combination form, I'm going to write it is 9i plus 5j. Number 2 is pretty similar. It's asking us to find the component form and the linear combination form. The initial point is 1, 8, and the terminal point is 3, -7. So I'm not going to graph it out this time. I'm just going to go ahead and do the terminal, which was 3, -7, minus our initial, which is 1, 8. So I'm going to go ahead and do 3 minus 1, -7 minus 8, which would be 2, -15. If I was writing this in linear combination form, I'm going to write 2i minus 15j. Okay, and if they give us the initial and the terminal point, finding either of these two forms is not very difficult. It doesn't get harder than this. Okay, and just to remind us how to read this, this is just telling us the direction that this particular vector is going. It's telling us it's going to the right 2 and down 15. Moving on though to number 3, we see this brand new term. It says determine the magnitude of the vector v with initial point 4, 6 and terminal point 7, 2. So I'm going to zoom in, literally zoom in, but we're also going to figuratively zoom in on this word and just kind of examine that. Magnitude means the length. And the way that we see this is denoted with, it kind of looks like our parallel line symbol on both sides of the vector. So we'll see like the 2 lines and then a bold variable and then the 2 lines. So that is our notation for length or for the magnitude of a vector. So some of you may have been wondering up to this point, yeah, this is great and all, but why are we doing this in this chapter? How does this connect to dealing with triangles? And we're going to kind of see that in this particular problem. So they give us the initial and the terminal. They do not give us any other information. So even though they don't ask me to find the component form, that's actually the first thing I'm going to do. So I'm going to do 7, 2 minus 4, 6. And the reason why I'm going to do this is because I actually want to see what this looks like. So I end up getting 3, negative 4. And I'm going to draw myself a picture. Now, I don't need this picture. I don't even know why I'm putting it on a graph here. The whole point is, if I know what's happening, I don't care about the actual values of it. I just know that there is some sort of triangle where we're moving to the right, and we're going down. Okay, so we're going to the right 3, we're going down 4. So this is our initial point, this is our terminal point. So I'm going to go ahead and just kind of show that. And so this is where our vector actually is. So the length of this vector is going to be the hypotenuse of this right triangle. And the good news, we can bring back our favorite theorem, the Pythagorean theorem. And even though we probably know this value off the top of our head, we know that the hypotenuse squared equals the sum of the square of the two legs. So some of you guys recognize this looks like one of our Pythagorean triples. And we end up getting that the magnitude is V. So just to sum up what we've done so far, we've learned how to find component form of a vector. This tells us really the direction that it's taking. In this case, it's going to the right 3 and down 4. The magnitude is the length, and that's the hypotenuse of this triangle that's formed by having a horizontal component and a vertical component. The way that we find the measure of the magnitude is by using the Pythagorean theorem. Now that's something we need to know, but I don't necessarily think that's something we need to spend time memorizing, because we should already be pretty well versed in using Pythagorean theorem. Number 4 looks at things a little bit different here. Okay, so we're kind of transitioning, and you're going to see we're going to do a bunch of stuff with vectors today. It tells us vector u, and it writes it to us in linear combination form. It also gives us vector w in linear combination form, and it tells us v is 3 times vector u minus 2 times vector w, and we want to find the component form of vector v. So this can look a little bit confusing, but it's actually going to be one of the easier problems we have to deal with. The first thing I'm going to do is rewrite vector u as 3, 2, and vector w as 1, negative 1. I just think it's easier for us to see it in that light. They tell us that vector v is 3 times vector u minus 2 times vector w. So I'm going to say vector v is 3 times 3, 2 minus 2 times 1, negative 1. And even though these are component forms and vectors, we're going to go ahead and multiply everything in that first component form by 3. So I would get 9, 6, and I'm going to multiply everything in that second one. I could either multiply by a negative 2 and make it positive here, or I could multiply by 2 and leave subtraction. Either way is fine. Okay, so I multiplied this whole negative 2. So when I add together my like terms, I get 7, 8. So what that tells us about this vector is it's moving to the right 7 and up 8. If we wanted to find the magnitude, which they're not asking us to do, we could use Pythagorean theorem and find the length of the hypotenuse. Number 5 looks pretty similar. The first thing I'm going to do, apparently I cannot speak, I'm going to make u into 4, negative 3, and w into 1, negative 1. That's just converting it from linear combination form to component form. Vector v is 2u plus 3w. So I'm going to go ahead and say 2 times 4, negative 3, plus 3 times 1, negative 1. So I have 8, negative 6, plus 3, negative 3, which is 11, negative 9. Don't make vector operations harder than this. This really is as easy as it is when we're dealing with just multiplying by a constant value. It makes it pretty straightforward. Okay, number 6 gives us a brand new term that we need to kind of delve into. It says find a unit vector in the direction of v equals 3i minus 2j. A unit vector, you guys have heard that term unit before when we talked about a unit circle, and they are connected to one another. A unit vector has a magnitude of 1. That means when we draw it out, its length is 1, just like how the unit circle has a radius of 1. Okay, so with that in mind, the way that we actually determine it, a unit vector is a vector divided by its magnitude. So this is definitely a formula that we need to know. So in this particular case, the first thing I need to find, I'm going to write the component form of vector v, which would be 3, negative 2. If I go ahead and draw a picture, it's moving to the right 3 and down 2. Notice this does not need to be to scale, but I'm going to say that this is the magnitude of v. So the magnitude of v squared equals 3 squared plus negative 2 squared. So I get that the magnitude of v is equal to radical 13. And unfortunately, we really cannot simplify radical 13 at all. So now what I'm going to do, I need to do the vector divided by the magnitude. Our vector is 3, negative 2, and I'm dividing by a magnitude of radical 13. And just like multiplying and adding vectors was pretty straightforward, so is dividing. We just need to divide both parts of the component form by radical 13. So I have 3 over radical 13 comma negative 2 over radical 13. Now we know from many years of dealing with radicals that we should not leave that as our final answer. I should rationalize it. So I would get 3 radical 13 over 13, negative 2 radical 13 over 13. And just to review, what we really did there was multiply by radical 13 over 13, radical 13 over radical 13. So this would be a unit vector for that particular given vector. Now, we said that the magnitude ends up being 1, and you guys definitely do not need to do this, but I want to kind of check that out. So we said that to find the magnitude, we're really finding the square root of the sum of these two sides. So I'm just going to say that when I square them and add them, it's equal to the magnitude squared. Okay, so when I square this particular expression, I get 9 times 13 over 169 plus 4 times 13 over 169 equals the magnitude squared. When I go ahead and add these numerators together, I get 169. We know our common denominator is 169. So I get 1 is the magnitude squared, so 1 is the magnitude. Now we definitely do not need to do this to prove what a unit vector is, but I just wanted to demonstrate that we could double check our work every single time by making sure that when I find the magnitude of the unit vector, that our final answer there is 1. Number 7, we have another unit vector problem. So I'm going to start by saying the vector is 4, negative 2. And so if I'm drawing this out, I'm going to the right 4 and down 2. So I'm going to use Pythagorean theorem and say the magnitude squared equals 4 squared plus negative 2 squared. And so I get that the magnitude is equal to radical 20, which when I simplify, I get 2 radical 5. So now we're going to go ahead and do the vector divided by the magnitude. So I have 4, negative 2 divided by 2 radical 5. So I'm going to do 4 over 2 radical 5, comma, negative 2 over 2 radical 5. And I see that this simplifies to 2 over radical 5, or 2 radical 5 over 5. And this simplifies to negative 1 over radical 5, or negative radical 5 over 5. Okay, so once again, the unit vector is the vector divided by its magnitude. Let's do one more magnitude problem before we jump into our next set of notes. Yes, we're not done yet, as you probably saw when you saw how ginormously long this video actually is. So, to find the magnitude, I'm going to start by doing terminal minus initial. So I'm going to do negative 1, 10 minus 2, 5. So I get negative 3, 5. So that's telling me we're going to the left 3, and I should actually draw this down here. So I'm going to the left 3 and up 5. So there is our magnitude. So to find our magnitude, I'm going to say the magnitude squared equals negative 3 squared plus 5 squared. So I have the magnitude squared equals 9 plus 25. So our magnitude ends up being radical 34. There's actually nothing else we can do with 34 to simplify it. So when we talked about direction earlier, we talked about direction with a horizontal and a vertical component. Now what we're going to actually examine is the direction being the angle away from 0 degrees. So the direction really here is talking about an angle. So the first thing I want to point out is that our angle is always going to be positive. And this is going to be one of those circumstances that you are smarter than your calculator. I actually think you guys are always smarter than your calculators, but here our calculator can possibly lead us astray. So let's go ahead and kind of draw this out based on what we know about this particular vector. I know that our component form would be 7, negative 2. So if I'm trying to draw this out, 7, negative 2 would be in quadrant 4. Now keep in mind, I don't care if I'm drawing this accurately in terms of the initial and the component form. What I care about is the direction that we're actually moving in here. So I'm going to somehow draw this ray, this vector, into quadrant 4. And we're going to say it's moving to the right 7 and down 2. Now, we have actually spent a lot of time dealing with finding angles. In fact, some of you guys were so excited probably when you saw that we didn't have triangles at the beginning of today. But we're kind of back to this. And my goal here is I really want to figure out how far away are we from 0. But that's not part of our triangle. What is part of our triangle is this reference angle. And we've learned previously, yes, we're using previous knowledge here, that if I find the tangent or the inverse tangent of this angle, I can set it equal to the opposite over the adjacent. So I'm going to say tan of alpha equals negative 2 over 7. So in my calculator, just to review, I'm doing tan inverse, negative 2/7, and I end up getting something kind of strange. I get negative 15.9 degrees. And I want to talk about what this means. Okay, we learned on the very first day of trigonometry that all a negative means is the direction. So it would actually make sense, I know negative goes clockwise, it would make sense that this is negative 15.9 degrees because it's not moving a ton, but it is moving clockwise. So if this is 15.9 degrees, how are we going to find the rest of this? Well, this is just like finding reference angles when we are dealing with special triangles. So since this is in quadrant 4, I'm going to do 360 because that is this entire circle. And I'm just going to subtract this little piece that we know. And if I do 360 minus the piece that we know, it gives me the angle that we need, 344.1. This is an angle that makes sense to me because if I drew this in quadrant 4, I know that my angle of direction should be between 270 and 360, so this angle is accurate. Okay, what we're going to do on all of these is pretty similar. The only thing that's really going to differ is how we actually find the angle. So, like number 2 here, -1, -4. I know that that is going to be in quadrant 3. So there's -1, -4. You can see that this definitely is not to scale. We want to find this time how far away is it from 0. So what it looks like we're going to have to do is find this angle inside here and add 180 to it. So I'm going to say tan, and I used alpha, but we can use whatever we want, equals -4 over -1. So in my calculator, I'm doing tan inverse, and I'm just going to write that as 4. And I get 76.0 degrees. So if this little piece is 76.0, that means I can do 180 plus 76.0, and I get 256.0 degrees. So every single time we're going to be using tangent, and that's similar. The thing that's going to vary is based on what quadrant we're drawing in. We're really going to have to think about how could we find the angle from 0. Obviously in quadrant 1, just so you guys know, it's the easiest because I just need to do tan and that's my angle. So we've kind of seen what happens in quadrant 4, quadrant 3, and now we're going to do quadrant 2. So this is moving to the left 2 and up 5. This time I want to find this angle, so it looks like we're going to have to find the angle inside the triangle and do 180 minus this little piece, and that'll give us our angle of direction. So I'm going to say tan of alpha equals 5 over -2. When I put tan inverse of 5 over -2 into my calculator, it gives me a negative angle again. Okay, but let's think about this. Once again, what it's telling me is that from this origin, it's moving in a clockwise direction, 68.2 degrees. So we can just kind of throw away that negative. It's just telling us a direction, which we can see with our own eyes that it moves up, it moves clockwise. Okay, so we don't even need the negative to tell us that. To get our final answer, I'm going to do 180 minus 68.2 degrees. And I'm not subtracting because it's a minus there. I'm subtracting because I need to take this whole part minus a little piece to figure out what the other piece is going to be. And I end up getting 111.8 degrees as my final answer. Number 4 is a little bit different. Okay, they're asking us to find the component form, which is something we're familiar with now, but it's not giving us any of the information we're used to. It's not giving us the linear combination form. It's not giving us a terminal point and an initial point. What it's doing, it's giving me a magnitude and a direction. So I'm going to start where I always start if I don't know what to do and kind of sketch a picture of what this is going to look like. So the fact that it's 120 degrees tells me that I should go in quadrant 2. Okay, so I'm going to pretend this is my vector. This is the 120 degrees, so I know that my reference angle is actually 60 degrees. They tell us the magnitude is 8. That's a weird looking 8. Let me rewrite it. Okay, the magnitude's 8, so that's the hypotenuse. We're trying to find x, which is really my horizontal part, and y, which is my vertical component. And so if we look at this, it looks like to find x, we're using the adjacent and the hypotenuses. So I know that cosine is what deals with adjacent and hypotenuse. So I'm going to say 8 times the cosine of 60 degrees is equal to x. And when I go ahead and do that in my calculator, it's going to give me a positive value. It's going to tell me positive 4 is x. However, we can clearly see x here is moving to the left, so it should be a negative 4. In fact, if you guys put in 8 cosine 120, it will tell you negative 4. Okay, so we will eventually get to that, but I'm just trying to break it up piece by piece here. To find y, it looks like that's the opposite over the hypotenuse. So I'm going to do sine of 60 equals y over 8. So I get 8 times the sine of 60 equals the y value. And when I put that into my calculator, I get 6.9 equals y. And that value makes sense to me because it does appear like it is going up. Now, if we want to, we could draw it out every single time. But I notice a pattern here. And I'm seeing that to find that x component every single time, we're going to do the magnitude times the cosine of the angle given to us. To find the y value every single time, we are going to do the magnitude times the sine value that's given. So this is a formula that we should memorize. So let's go ahead and do another one. Number 5, it tells us V has a magnitude of 200 and direction of 215, and W has a magnitude of 150 and a direction of 162. And then we need to find V plus W. So it's kind of asking me to do 3 things at once. So I'm just going to start with vector V. Okay, to find component form of vector V, I'm going to do the magnitude of V times the cosine of theta, comma, the magnitude of V times the sine of theta. And we will see sine often goes with the y value. We saw that last semester, we will see that to come. So in this case, I would say 200 times the cosine of 215, comma, 200 times the sine of 215. And for those of you that are super visual learners, it might be helpful if you go ahead and kind of draw this out every time like we did on number 4. But we really don't need to do that. We can just use this formula. I end up getting, in this case, negative 163.8, comma, negative 114.7. Okay, now we're going to deal with W. And this time with W, it told me that the magnitude was 150 and that the direction was 162. So I'm going to do 150 cosine 162, comma 150 sine 162. And when I put this into my calculator, I get negative 142.7, comma 46.4. So now we need to go ahead and find V plus W. So if I'm doing V plus W, I'm going to take these 2 values and add them together. And I get negative 306.5. Then I'm going to take the 2 y values and add those together, and I get negative 68.3. So that would be our final answer. 6 is really similar, which is just good for us to practice this, so let's go ahead and do it again. Okay, they tell us this time vector V has a magnitude of 150 and a direction of 30. So I'm going to go ahead and use that information to help me find the component form. And I'm going to go ahead and put this into my calculator right now. Just a reminder, just like everything else this chapter, notice our mode should be in degrees. So I'm going to do 150 cosine of 30, and I get that that is 129.9. And then I'm going to do 150 times the sine of 30, and I get 75. Okay, for vector W, it tells us the magnitude is 75 and the direction is 206. So I'm going to say 75 cosine 206, 75 sine 206. So I get negative 67.4, negative 32.9. And if we think about these, and I didn't really talk about this earlier, but this would make sense for vector V because it is in quadrant 1 because it's 30 degrees, so it would be positive and positive. 206 is in quadrant 3, so it would make sense that both of these are negative values. So now to figure out what we're calling, we don't even call it anything. We're just saying we need to add those together. So I'm going to do 129.9 plus negative 67.4. And I end up getting 62.5. And then I'm going to do 75 plus negative 32.9. And I get 42.1. Now, if we actually graphed these vectors on top of each other, this is what would happen. Okay, so graphically, if I started one where the other one ended, it would end up going to the right 62.5 and up 42.1. I'm actually going to skip 7 and 8 because I feel like they are doing the exact same things that we've been doing. Okay, number 7 is finding a direction, so that's like 1, 2, and 3 on this set of notes. The other one is finding the component form, which is what we just did a ton of. And I'm going to just skip to the last problem here, which is number 9. And I want to go through this one because it is a little bit different. Okay, it tells us that we have a vector that has a magnitude of 8, but we want to find that vector in the same direction as vector u. So we're going to use that same concept of using the magnitude times cosine of the angle and all of that, but we need to find this angle first, and then we're going to throw that away. All we care about is the angle. I don't care about 7, 4. So I'm going to go ahead. This is in quadrant 1. It's going to the right 7 and up 4. And this is the one that I kind of told you earlier is the easiest because this is actually the angle we want to look for. So I'm going to say tan of alpha equals 4 over 7. So tan inverse of 4 over 7 equals, I'm typing this in right now, 4 divided by 7. And I get that that is an angle of 29.7 degrees. I care about that. I don't care about any of that other work anymore. Now we're just using that the magnitude is 8 and the angle is 29.7 degrees. Now we need to find this new vector. So we're going to do the magnitude times the cosine of 29.7, the magnitude times the sine of 29.7. So notice that in this problem, we're really not doing that much work that's different. We're just kind of combining a few different concepts. So I get that this is 6.9, and when I do 8 times the sine of 29.7, I end up getting that that is 3.96 or 4.0. Okay, so today was an intro to vectors. I know we covered a lot of concepts. Hopefully we're feeling pretty good on how we're using these basic trig values and trig ideas that we've learned in previous chapters and apply them to this brand new concept.